Hi, this is a video recording of the project for the Wireless Communication course at the University of Florida. I am Suchitra Chandran and my project is titled Comparison and Analysis of LDPC Coder and Decoder Algorithms. The contents of the presentation are as follows. We begin with the introduction, followed by the motivation and the prior work done in this domain. We discuss the implementation of the encoder and the decoder and the results, conclusion, followed by the future work. Since the runtimes of the program are high, we modify the input parameters to suit the timing constraints of the video. So let's begin the run. So we have an m cross n of 300 cross 600 for an iteration of 5. Moving ahead with the introduction. With the increase in the amount of information being carried in the channel, there is an increased need for reliable yet efficient communication. The data transmitted through the channel is subjected to various forms of corruption because of the noise in the channel, transmission error and decoding error. Error controlling codes have been introduced. They introduce redundancy in the transmitted message and alleviate the need for retransmission. The figure here depicts an ECC communication channel. You have an information source, a source encoder, an ECC encoder, a modulator. The channel here introduces corruption followed by a demodulator, ECC decoder, a source decoder to extract the data, and an information sink. The different types of ECC codes are the turbo code and the LDPC code. Though the error correcting performance of the turbo codes were the best, they were not favored because of the decoding complexity and high latency. For applications that require high data rate, LDPC was considered as a better pick over the turbo codes. They used lesser iterations and had increased throughput. The challenges involved in the implementation of the LDPC code lies in the implementation of its decoder hardware. If the decoding of large matrices were considered, then the parity check matrix makes wiring between the variable nodes and the check nodes more complicated, leading to routing congestions and reduced speeds of the decoder. The motivation behind this paper, LDPC convolution-based coding versus LDPC block-based coding, it showed that the convolution-based coding performed better even though they were derived at low rates. Gallagher developed the LDPC code in the early 1960s. He developed the belief propagation decoding algorithm and also introduced the bit flipping decoders. He introduced the Tanner graph. So this is a representation of a Tanner graph. The circles represent the bit transmitted and the squares with the plus symbol, they represent the parity check constraints. These plain squares, they represent the information associated with each bit. In the belief propagation algorithm, messages are passed between the parity check nodes and the bit nodes. The bit nodes send their belief to their neighboring values and the check nodes evaluate these messages and send messages accordingly as the response. The decoding algorithm can either be hard decision based like the bit flipping algorithm which is based on a threshold, or it can be soft decision based which can be based on probability or logarithms. Moving ahead with the methodology, let's first look at the implementation of the encoder. The encoder implementation is divided into two stages. The first stage involves the LDPC matrix creation. The inputs to this portion of the code involves the number of rows, the number of columns, the number of ones per column, and the number of iterations of the decoder. The even mode method is used that ensures that the rows and columns have the same number of ones, after which ones are added to the rows that have only a single one or have none of the ones. At the end of this algorithm, you have a parity check, an LDPC matrix of size n cross n. It's a parity check matrix basically, and it's represented as H. Next, we move on to looking at how we generate the parity check bits. H can be represented as PQ, and P is decomposed into L and U, where L represents the lower triangle and U represents the upper triangle. This algorithm here, it shows how the decomposition of P is done into L and U matrices. L and U are initially assigned to null matrices. We assign H to F and you run I from 0 to M. You find the non-zero element in the row and column I of F. You place the element in the row and column I, and then you rearrange matrices F and H. These steps over here involve the rearrangement. Rows that have the value 1 in column I have row I of F inserted. This process continues till this value expires, value of I crosses M, and then this algorithm ends here. The minimal product strategy is what is used to select the non-zero element for the diagonal. The choice is based on the element that minimizes the product of the quantity of non-zeros in its rows -1 and the quantity of non-zeros in its column -1. Decoder. Now you have a parity check matrix H of size n cross n. You have the row weight, you have the column weight, and you have a BPSK modulated signal, which is the LDPC code of the LDPC code. The various algorithms that I use. Okay, now this is our output of a 300 cross 600 matrix. Let's change the code and run it for 250 cross 500. Okay. So the various algorithms that were studied as part of this paper were the bit flipping algorithm, the log domain based sum product algorithm, and the probability domain based sum product algorithm. The bit flipping algorithm. This algorithm primarily is based on the check that if the unsatisfied parity check equations, the number of unsatisfied parity check equations exceeds a fixed threshold value, then the bit is flipped. This is the primary implementation idea. So we start by calculating the parity check equations. If the equations are fulfilled, then the algorithm ends because the value is being decoded. If it's not fulfilled, then you for each bit compute the amount of unfulfilled parity check equations, and for each bit, if all the equations associated with that bit are unsatisfied, then the bit is flipped. The strengths of this algorithm are: it has a high speed of decoding. This is primarily because it uses simple operations like XOR to perform the decoding, and it uses the data which is stored in a single bit. The flipping threshold must be chosen very wisely, because if the value is too large, then the algorithm works conservatively, taking an enormous amount of time to converge. But if the value is too small, then it works very aggressively and it might flip the correct bits. Moving ahead to the log domain based sum product algorithm implementation, the modulated code word is represented by X bits, the data received is represented by Y bits, the variable nodes are represented by VI, check nodes are represented by CJ, VI/J represents the variable nodes in VI other than J, CJI represents the check nodes in CJ other than I, alpha ij represents a message from the check node I to variable node J, and beta ij represents a message communicated by variable node J to check node I. Lambda here represents the information from the log likelihood ratio of 5, and can be represented by this formula. And this is the algorithm which is used to describe the log domain based sum product algorithm. There are a number of formulas here. Though these formulas are not clear over here, it is more visible in the paper. So for each value of I and j, beta ij is initialized to the log likelihood value of the received vector. Alpha beta values are calculated and are transferred between the variable and check nodes in each iteration. Beta messages for every variable node is used for computing alpha ij. Using this formula, we compute alpha ij. So now this is the output which we got for n cross n, which is 250 cross 500. So let's now that was 250 cross 500 and iterations were 5. Now let's run it for 4 iterations and check the results. So as I was explaining, beta messages from every variable node is used to compute alpha ij, and alpha ij is calculated using this formula here. The channel information and alpha messages can be used to compute the beta ij. The beta ij value is calculated using this equation here. The channel information and alpha messages from neighboring check nodes are added to each bit in the column j and are updated using this formula of zj. The estimated code vector, which is represented by x bits, is calculated from the updated vector by this updation here. So xi can either take the value of 1 or 0 based on the value of z. And to check if the calculated code is valid, the following condition, that is h dot x transpose should be equal to 0. If it is equal to 0, then the decoding has happened correctly and the algorithm has completed the decoding process. The advantages of this decoding process is that it requires lesser quantization levels and it is less sensitive to quantization effects. It does its computation based on message additions instead of message multiplications, and it takes lesser number of clock cycles, thereby saving more power. and power dissipation is also reduced. The last decoder algorithm which is discussed is the probability domain based sum product algorithm. N independent binary digits AI are considered and their probability is given by PR. The message passing algorithm of the a posteriori probabilities is initialized with Qij of B for all values of ing that satisfy the equation Hij is equal to 1. This is the flowchart representing this algorithm. So you run I from 0 to n minus 1. You set the values of Pi and Qij of 0. You update the value of Rji of B using these equations, which is Rji of 0 and Rji of 1. After which you update the value of Qij of B using these equations. So you have Qij of 0, you have Qij of 1. So let's minimize this and keep. You have Qij of 0 and you have Qij of 1. In this step, for every value of I ranging from 0 to n minus 1, you calculate capital Qi of 0 and Qi of 1, and the value of the constants Ki is chosen such that the sum of these is equal to 1. For I ranging from 0 to n minus 1, you calculate the value of C cap I. The termination condition checks if C cap H transpose equal to 0 or the maximum number of iterations are achieved. The advantage of this probability domain based sum product algorithm is that it's able to detect an uncorrected code word with the probability near unity also. Okay, now we're ready to discuss the results. The various experiments that were performed were based on varying the size of the parity check matrix to understand the effect it has on the implementation. We vary the number of iterations of the decoding. The performance comparisons of the algorithm was done to understand which algorithm performs better. So by varying the parity check matrix, we saw that if we vary it from 2000 cross 10,000 to 500 cross 1000 and 250 cross 500, the performance actually shows a significant difference. So computation time involved when your matrices are larger is high, and the decoding rates improve with the increase in the size of the parity check matrix. Now let's check our results here. So the first result which we ran was for 300 cross 600, and the second result that we ran was for 250 cross 500. So if you see here, the performance of the 300 cross 600 is much better than the result of 250 cross 500. So greater the size of the parity check matrix, though the computation time involved would be high, the performance would be much better. Similarly, when the number of iterations increased, we saw that the performance of the BER was much better. So this is the one which has been run for 5. You have 250 cross 500 as the size of the parity check matrix, and it has been run for 5 iterations, and the performance was seen to improve extravagantly. So this is the graph which depicts the iterations of 4. We ran it for 4 iterations, and that is figure 5. Figure 5, yes. Figure 5 and figure 6. Okay, so this was this ran for 5 iterations and this ran for 4 iterations, and we can see how the performance has improved in this case. Moving ahead, we see from our analysis that the bit flipping algorithm performs the worst because it requires high decoding iterations to actually perform better. The probability domain algorithm performs much better because it requires lesser decoding complexities. Bit flipping algorithm has the worst BER, and log domain and probability domain SPA perform competitively. Increase in the number of iterations improves the decoding, and increase in the size of the parity check matrix increases the computational complexity. The future work, this project can also be extended by increasing the number of ones and checking its implementation. We can implement the weighted bit flipping algorithm to check the improvement, and we can perform variations in the parity check size matrix to find the most suitable configuration size. Thank you.